Here's problem number 13 from chapter 5. In it, we have this picture here. An 11-kilogram salami is supported by a cord that runs to a spring scale, which is supported by a cord hung from the ceiling. What is the reading on the scale, which is marked in weight units? And then next, we look at this one. It's supported by a cord that runs around a pulley into the scale. The opposite end of the scale is attached to a cord on the wall. Now, what's reading the scale? And in our third situation, we have two salamis hanging by both ends of the spring scale. The assembly is stationary. What is the reading on the scale? So this problem is mathematically quite simple, but conceptually kind of tricky. It's hard to understand. So first we'll start with part A, because that one I think is the most intuitive. And so I'm just going to draw a free body diagram of my salami. So here's my salami. I have the weight of my salami going down and the tension going up. And the important thing about this is that the tension, which is in this rope right here, is what the spring scale is reading. And so we know that it's not accelerating. We know that the sum of these forces will equal 0, but we can solve for this. And so the tension will be equal to our weight. So the force due to gravity, which is our weight, is mass times acceleration, but in this case, it's mass times gravity, because that is our acceleration. So our mass is 11 kilograms, gravity is 9.8. So if I multiply those two things, I will find out that my weight, and therefore my tension, and therefore the reading in the spring scale is 108 newtons. And this hopefully is something that's a bit intuitive, because if you're hanging something from a spring scale, you are measuring its weight. And so that is its weight, and that's what we're measuring. The reason I bring up the tension here is because that's going to apply very much over to these situations. So this is part A, but now in part B, we again have the weight from our salami and our tension right here. Since we're not moving, we know that the sum of both of these forces must be equal. And so this weight must equal this tension. Both of them must be 108. Otherwise, my salami would be moving up or down. And so since this is going over a frictionless pulley, I know that the tension at all points in here must also be the same. So the tension everywhere is 108. Whenever I'm drawing tension, I will always draw it going away from the object at hand. And so I'll draw it going away from the salami. I will draw it going away from my spring scale. And so, but this tension is the exact same thing as that tension right there. So this tension is 108 newtons, which is the reading in my spring scale. And so for this, it's the same thing. Our answer is 108 newtons. I think that this one is somewhat intuitive. It's more tricky than this, but I think students seem to be okay with this one. Once we get to part C, it seems to get a little bit crazy. So I have two salamis hanging. I want to know about the spring scale. Now, here's the deal. We know that our whole situation is not moving. It's not accelerating in any direction, just as this one was not accelerating in any direction. I know that the weight is still 108 newtons. This is the same identical salami over here, so I have 108 newtons over here. But what I do know is that if I were just to come and hold this rope right here, then I would have the exact same situation as what I do now. So essentially what's happening is that our wall is pulling our spring scale with a force of 108 newtons, just in the same way that our salami is pulling with 108 newtons. Now, some students are like, wait a second, I have a tension here of 108 and a tension here of 108, so shouldn't I have a force of 216? But no, the answer is actually going to be 108 newtons again. And here's how you can think about it. The only way that I'm able to read this 108 newtons pulling on my spring scale is the fact that I have a force pulling back on my spring scale. That's exactly what happened here. You're holding the spring scale up with a force of 108 newtons. The wall is pulling it back with a force of 108 newtons. There's no situation in which I can just hook a salami onto a spring scale and let it go, because it would just fall off the counter unless it's being held back by an equal and opposite force. And we know that they're equal because we're not accelerating, but in fact, these pulling on either end will give us the reading of 108 newtons right there. So to reiterate, this situation is almost identical to this one, except instead of the wall holding it, the salami is holding it. And so we end up with the same reading on all three spring scales of 108 newtons.